Okay, this is part 2 of our previous question. Let's record significant values that we've already done. The moment of inertia for the disk was 563 kilogram meters squared, and the I for the girl was 470 kilogram meters squared. And we found the final velocity once we accelerated the rotating platform, and that was an omega. And I'm going to label that as omega 1 for right now, because that will be our omega 1 for this example, is 3.1 rads per second. Okay. And again, that was omega 2 for the previous question, but we're going to be using the equation I1 omega 1 equals I2 omega 2. And the reason is, once the girl accelerated in the previous question to this value of 3.1 rads per second, the applied force is removed, and then she is going to move inward. Okay, and she's moving until she is 0.5 meters from the center of rotation. So we're going to need to recalculate her new moment of inertia. Okay, and we'll do that right here. So her new moment of inertia I is going to equal 60 times 0.5 squared. Okay, and the new moment of inertia is now going to be 15 kilogram meters squared. The idea is, as she moves in, it'll cause the rotating platform to go faster. Okay, because the moment of inertia is going to go down. And this equation is our conservation of angular momentum equation. So plugging in our I1 will still be the 563 plus the 470. And we will multiply that, okay, by the 3.1. And again, that's the answer from the previous question. We'll set that equal to I2. And that'll be 563 plus 15. Notice how the 470 now is 15. And then we'll multiply that by omega 2. And omega 2 is 5.5 rads per second. And again, you see that the angular velocity of the rotating platform has increased because she has lowered the moment of inertia of the whole system. Now, again, we don't get anything for free in physics, so she has to pull herself in. So she's applying a force through a distance. So the force from 2.8 meters, okay, into through a distance all the way to 0.5 meters. So we want to find the work done as she does this. We don't know what her applied force is, but we do know that conservation of energy has to be valid. The work done as she pulls herself in has to be equal to the change in rotational kinetic energy for the system. So to find the work done, I'm going to label work is equal to the change in kinetic energy rotational. So let's calculate that here. So the work is going to equal 1/2. Now we'll add these two together and have omega 2 squared. So 1/2. 563 plus 15 multiplied by 5.5 squared. And we'll subtract 1/2 times 563 plus 470 times 3.1 squared. Okay, now again, what we're doing is we're taking the rotational energy final minus the rotation or kinetic energy initial. And the work done then is equal to 3,780 joules. This again is equal to the change in rotational kinetic energy for the system as the girl pulls herself in towards the center.